Good morning and welcome to the lecture number 6 of the course Water Resource Systems, Modeling Techniques and Analysis. We are introducing the systems techniques now, which means essentially we are talking about optimization techniques to begin with. Subsequently, we will go to the simulation and other stochastic optimization and so on. So, right now we are talking about deterministic optimization. We started with optimization of a function of single variable without any constraints. So, we specifically dealt with unconstrained optimization, and so we started with functions of single variables, extended the optimization to functions with multiple variables without any constraints. And in the previous lecture, we started introducing constraints to the optimization problem. So, we are now entering into the domain of constrained optimization. And in the previous lecture, we introduced a general form of the optimization problem, where you have minimize or maximize f of x, where x is a vector of decision variables x 1, x 2, etcetera, x n, and subject to the conditions g j of x less than or equal to 0, where g j of x are the set of constraints j is equal to 1, 2, etcetera, up to m number of constraints. So, we are dealing with n variables and m constraints. In general, m is less than or equal to n. In this general class of optimization problems, we started with equality constraints. That means, g j of x is equal to 0. So, we dealt with in the previous lecture a maximization of a function subject to equality constraints, and typically we introduced two different methods of dealing with equality constraints. One is the direct substitution, where you will express n minus m number of variables in terms of the remaining m variables. I am sorry, I will repeat. We express m variables in terms of the remaining n minus m variables and convert the constraint optimization problem into an unconstrained optimization problem with n minus m variables, and then solve using any of the techniques that we have dealt with earlier. This is called as a direct substitution method, and the direct substitution method is useful when you have less number of constraints and the substitution is fairly straightforward. If you have highly complex non-linear constraints, or if you have a large number of variables, then this kind of direct substitution will not in general be feasible. Then we introduce the Lagrange multiplier method, where associated with each of the equality constraint, we add a variable called as the Lagrange multiplier. So, g j of x equal to 0 is the equality constraint that we are talking about. Associated with each constraint g j of x, for each j, we associate a Lagrange multiplier named as lambda j, denoted as lambda j, and then we formulated the necessary conditions and the sufficiency conditions. We will continue the discussion now with the Lagrange multipliers. So, this is a summary of the previous lecture. We introduced the constraint optimization, where we are talking about minimization or maximization of a function f of x subject to g j of x less than or equal to 0. This is a general form of the optimization problem, and we dealt with functions with equality constraints, that is optimization of functions subject to equality constraint. So, the problem statement will be maximize or minimize f of x subject to g j of x equal to 0, and you have m number of such constraints, and x, remember, is a vector of n variables x 1, x 2, etcetera, x n. So, there are n number of variables, m number of constraints, and in the direct substitution we used m variables and expressed these m variables in terms of the remaining n minus m variables, and therefore, converted the original problem of n variables with m constraints to a new problem of n minus m variables without any constraints. So, we essentially in the direct substitution, we reduce the constraint optimization problem with to a unconstrained optimization problem, and in the process we are also reducing the number of variables, because we have been able to express the m variables in terms of the remaining n minus m variables. However, this is useful only in very simple cases, and in most engineering problems where the problem size is huge and the nature of the constraints is quite complex and often non-linear, you have often non-linear constraints, then the direct substitution method is not elegant. We introduce the Lagrange multipliers where associated with each of these constraints g j of x is equal to 0, we insert another additional variable lambda j, we introduce another additional variable lambda j. So, in the direct substitution method you reduce the number of variables, whereas in the Lagrange multiplier method you increase the number of variables. So, instead of the original n number of variables, you now have n plus m number of variables. The n original decision variables x 1, x 2, etcetera, x n, and the additional Lagrange multipliers lambda 1, lambda 2, etcetera, lambda m. And then we formulate the Lagrange L is equal to f of x minus summation j is equal to 1 to m lambda j g j of x, where g j of x is a original constraint, the left hand side of the constraint. Now, some places we use plus lambda j g j of x, it does not matter, because the sign of lambda j will be in that case different. So, the Lagrange function will be f of x plus summation j is equal to 1 to m lambda j g j of x in some textbooks. It does not matter whether you use minus or plus here. Starting with this Lagrange function, we introduce the necessary and the sufficiency conditions. We will continue the discussion from where we left last time. So, I will repeat the necessary conditions and the sufficiency conditions here, just so that the notations and the way we use the differentials is all correctly understood. So, the necessary condition for this is that we look at the Lagrange function. This is the original function f of x minus j is equal to 1 to m lambda j g j of x. This is the Lagrange function. For the Lagrange function to have a local minimum or a local maximum at x is equal to x star, the necessary conditions are that the first order differential of the Lagrange function with respect to each of its arguments, namely x 1, x 2, etcetera, x n, and lambda 1, lambda 2, etcetera, lambda m. The first differentials with each of these arguments must be equal to 0. So, dl by d x I is equal to 0 for I is equal to 1 to n number of variables, and dl by d lambda j is equal to 0 for j is equal to 1 to m. So, these will constitute n plus m number of equations, n equations here and m equations here. So, we use these equations and solve for the n plus m number of variables. What are the n plus m variables? X 1, x 2, etcetera, x n, and lambda 1, lambda 2, etcetera, lambda m. So, n plus m number of variables. So, we solve for x star and lambda star. Then we go to the sufficiency condition. For the sufficiency condition, we consider the second order derivatives of the Lagrange function L and the first order derivatives of the constraint functions g j of x is equal to 0. So, we look at the first order derivatives of the constraints and the second order derivatives of the Lagrange function. So, we define L I j is equal to d square L by d x I d x j, which is the second order derivative of the Lagrange function with respect to the variables x I and x j. This is defined for all I is equal to 1 to n. Then g j I, which is the differential of the jth function, jth constraint with respect to ith variable. So, we define g j I as dgj by dxi, which means the derivative of the jth constraint with ith variable, and this we define for all j's. So, once we have these derivatives, we formulate the determinant d as we start with L11 minus z, L12 etcetera L1n, which is here x1 etcetera xn, x1 etcetera xn. So, this is d square L by dx1 square, d square L by dx1 dx2 etcetera, d square L by dx1 dxn, and then we go to L21 etcetera L2n, Ln1 etcetera Lnn minus z. So, all the diagonal elements we introduce minus z here. So, this is n by n terms. This we formulate based on the second order derivative Lij. Then we introduce the next m terms here. This is the first partial derivative of the first constraint with respect to first variable, second constraint with respect to first variable, etcetera, mth constraint with respect to first variable. Then this is the partial derivative of the first constraint with respect to second variable, second constraint with respect to second variable, etcetera, mth constraint with respect to second variable, and so on. So, we get mth constraint with respect to nth variable. So, this will be m terms here and n terms here. So, this is a m by n component. We transpose this and put it here. So, we have n terms in this direction. So, we will have n terms in this direction and m terms in this direction. So, we transpose this and put G11, G12 etcetera G1n, then G21, G22 etcetera G2n in this direction, and similarly Gm1, Gm2 etcetera Gmn. So, these m by n terms we put it as n by m terms here. So, we are left with the last column, last corner, which has m by m terms. These m by m terms we substitute by 0. There is a proof available for why this has to be a sufficient condition for optimal. We will not go into the proofs, we will only use the final result of the proof and then see how we apply the sufficiency conditions for actual problem. So, this is the way we formulate the determinant d, and we evaluate the determinant d at the stationary point x star lambda star. Remember, we have determined x star lambda star by solving the n plus m equations, and we evaluate the determinant d at the point x star lambda star, and then equate the determinant d which is evaluated at x star lambda star to 0. When we do that, you get a polynomial in z. Remember, only z is unknown here, all other derivatives here are known and these are of course zeros. So, we get a polynomial of the order n minus m in z. We solve this for z and look at all the roots that we get for z. If all the roots of z are positive, that is greater than or equal to 0, then the point x star lambda star corresponds to a local minimum. Positive always corresponds to a minimum. If all the roots z are negative, then the point x star lambda star corresponds to a maximum. If some of them are positive, some of them are negative, then the point x star lambda star neither corresponds to a maximum nor to a minimum. That is the sufficiency condition. So, I repeat, we are dealing with function f, optimization of a function f of x subject to constraints gj of x is equal to 0. We introduce the Lagrange multipliers lambda j, one associated with each of the constraint gj of x. We formulate the necessary conditions by differentiating the Lagrange with respect to each of its arguments namely x1, x2, etc. xn and lambda 1, lambda 2, etc. lambda m, thus formulating n plus m equations. We solve the n plus m equations simultaneously to obtain the solutions x1, x2, etc. xn and lambda 1, lambda 2, etc. lambda m. Then we go to the sufficiency conditions. We formulate the determinant D as I just explained, evaluated at x star lambda star, equate determinant D equal to 0 and then you obtain a polynomial of the order n minus m in Z, solve the polynomial to obtain roots of Z. If all the roots Z are positive, then the stationary point x star lambda star corresponds to a minimum, local minimum. If all the roots are negative, then the point x star lambda star corresponds to a local maximum. If some of them are positive, some of them are negative, then the point x star lambda star neither corresponds to a maximum nor to a minimum. So, this is the method of Lagrange multipliers, and in fact, the Lagrange multipliers have some physical significance in terms of their ability to explain the sensitivity of the solution and so on. So, which we will discuss slightly later when we are dealing with the linear programming. But right now you just remember that lambda j's, which are the Lagrange multipliers, in fact have a physical significance. Okay, we will take this is what I just explained. So, if all z values are positive, then x star corresponds to a minimum. If all z values are negative, x star corresponds to a maximum. And then if some of them are positive, some of them are negative, it is neither a minimum nor a maximum. We will take an example now. Let us say we are looking at the maximization of the function f of x is equal to minus x1 square minus x2 square, subject to x1 plus x2 is equal to 4. In fact, the problem statement can be just optimize, that means maximize or minimize, subject to a equality constraint x1 plus x2 is equal to 4, because we do not know a priori whether the stationary point that we get after applying the necessary condition in fact leads to a maximization or a maximization of the function or minimization of the function. So, we just want to explore the optimal values, relative minimum, relative maximum of this particular function. So, this has one constraint, this has two variables, x1 and x2 are the two variables, x1 plus x2 is equal to 4 is the constraint. First, we express the constraint in the form gj of x equal to 0, which means the right hand side we make it 0. So, we express this as g of x, because there is only one function, one constraint, I write it as g of x is equal to x1 plus x2 minus 4 is equal to 0. So, we are writing g of x is equal to 0. And then formulate the Lagrange. Lagrange is f of x, which is the original function, minus lambda. In this case, there is only one constraint, therefore, I will use only one lambda, and therefore, I get rid of the subscript. Otherwise, I would have put lambda 1, lambda 2, etc. associated with constraint 1, 2 and so on. Because there is only one constraint, I will use lambda into g of x, which is x1 plus x2 minus 4. So, this is x1 plus x2 minus 4. So, this is the way we formulate the Lagrange. Once you get the Lagrange function, we apply the necessary conditions. So, at the stationary point, we want the necessary condition is dl by dx1 is equal to d0, dl by dx2 is equal to 0 and dl by d lambda is equal to 0. There are two original decision variables and one Lagrange multiplier. Therefore, we take 3 partial derivatives of the Lagrange function, and the Lagrange function L is minus x1 square minus x2 square minus lambda x1 plus x2 minus 4. So, dl by dx1 is 0, that leads to minus 2 x1 minus lambda is equal to 0. dl by dx2 is 0, that leads to minus 2 x2 minus lambda is equal to 0. And dl by d lambda is equal to 0 leads to the original constraint x1 plus x2 minus 4 is equal to 0. We are differentiating with respect to lambda. Then we solve these equations. Minus 2 x1 minus lambda is equal to 0, this is this equation, minus 2 x2 minus lambda is equal to 0 and x1 plus x2 minus 4 is equal to 0. So, we solve these equations to get x 1 is equal to minus lambda by 2 here and x 2 is equal to minus lambda by 2 here, and the third one yields x 1 minus x 2 plus 4 is equal to 0 or minus of x 1 plus x 2 minus 4 is equal to 0. You get from this, substituting x 1 is equal to minus lambda 2, x 2 is equal to minus lambda 2, you get lambda is equal to minus 4. And therefore, x 1 is equal to 2 and x 2 is equal to 2 is the solution. We then go to the sufficiency condition, for which we need to formulate the determinant D. Now, the determinant D is in this particular case L11, there are two variables and one constraint. So, L11, L12, L21, L22. This is a second order derivative of the Lagrange function with respect to the first variable, that is d square L by d x 1 square. This is d square L by d x 1 d x 2 and so on, and this is g 11, which is the first order derivative of the function g 1 of x with respect to the first variable, and first constraint with respect to second variable. Like this, we formulate the determinant and equate it to 0. So, dl by dx1 is as we have obtained earlier minus 2 x 1 minus lambda. Therefore, d square L by dx1 square will be minus 2, and d square L by dx1 dx2, this with respect to x 2, that is 0. Similarly, dl by dx2 we know as minus 2 x 2 minus lambda. So, d square L by dx2 square will be minus 2, and d square L by dx2 dx1 as before will be 0. And you have the constraint g of x, x1 plus x2 minus 4, g of x is equal to x1 plus x2 minus 4. This we differentiate with respect to each of the variables. So, dg by dx1 is equal to 1 and dg by dx2 will be equal to 1 also. So, with this now we formulate the constraint, we formulate the determinant, determinant D as L11. Look at this, L11 minus Z, L12 G11, and L11 is minus 2. So, minus 2 minus Z, 0, 1, and 0 minus 2 minus Z, 1, 1, 1, 0. So, this is the last m by m terms, which is 1 by 1 term here, which is 0. So, when we get the determinant and equate it to 0, you get 2 z plus 4 is equal to 0. You know how to get the determinant, and therefore, you get a solution z is equal to minus 2 here. In this case, you got a polynomial of the order n minus m, which is 2 minus 1, which is 1. So, you get a polynomial of order 1 in z, and therefore, in this particular case you get only one root, which is z is equal to minus 2, and z is equal to minus 2 is a negative root, and therefore, the point x star lambda star that you obtained corresponds to a maximum. So, as the root is negative, the stationary point x 2 2, which is x 1 is equal to 2, x 2 is equal to 2. What are these values? These are the values that we obtained by solving the necessary conditions. So, x 1 is equal to 2, x 2 is equal to 2. So, this is a stationary point. So, this stationary point x 2 comma 2, x is equal to 2 comma 2, which is x 1 equal to 2, x 2 is equal to 2, in fact corresponds to a maximum value, local maximum, and then we substitute the values 2 comma 2 in your original function, which is minus x 1 square minus x 2 square, and so here you put x 1 is equal to 2, x 2 is equal to 2, and you obtain the value as 8. So, the maximum value of the function is 8, subject to the constraint, that is the constraint that we considered. So, this is how we use the Lagrange multipliers to obtain the local minima, local maxima of a function of multiple variables subject to a set of equality constraints. Lagrange multipliers, the way we have introduced, is applicable only to equality constraints. Let us look at one more example. Let us say you take f of x. This is a exercise problem from a textbook, not solved exercise problem. So, I am solving that example now. F of x is equal to half of x 1 square plus x 2 square plus x 3 square, subject to two constraints, x 1 minus x 2 is equal to 0 and x 1 plus x 2 plus x 3 is equal to 1. So, these are the two constraints. There are three variables and two constraints. So, first, as I said, make the constraints of the form g j of x equal to 0. So, make the right hand side equal to 0 for the constraints. So, x 1 minus x 2 is equal to 0 is the first constraint, x 1 plus x 2 plus x 3 minus 1 is equal to 0 is the second constraint. So, this is the first step. We just express the constraints in the form g j of x equal to 0. Then we formulate the Lagrange function. We will take plus lambdas now instead of minus that we took last time. So, we formulate the Lagrange function by introducing one lambda associated with each of the constraints. So, we have two constraints and we put lambda 1 and lambda 2 as the two constraints. So, this is the original function f of x plus lambda 1 into g 1 of x plus lambda 2 into g 2 of x. So, this is how we formulate the Lagrange function. Then we apply the necessary condition by taking the first order derivatives of the Lagrange function with respect to each of the arguments. The arguments are x 1, x 2, x 3 and lambda 1 and lambda 2. So, we get 5 equations. So, dl by dx I is equal to 0, which will give 3 equations, and dl by d lambda j is equal to 0, which will give 2 equations associated with the 2 lambdas. And this is a L. So, dl by d x 1 is equal to 0 gives me x 1 here plus lambda 1 plus lambda 2 is equal to 0. I am differentiating with respect to x 1. Similarly, differentiate with respect to x 2, you get 2 x 2 here divided by 2. So, x 2 minus lambda 1 plus lambda 2 equal to 0. So, this is differential of s L with respect to x 2. Then with respect to x 3, 2 x 3 by 2. So, you will get x 3, there is no x 3 term here, and plus lambda 2 is equal to 0. So, you get 3 equations here 1, 2 and 3. Then we also differentiate with respect to lambdas, lambda 1 and lambda 2 to get the original constraints. Remember, when we differentiate the Lagrange with respect to the Lagrange multipliers lambda 1 and lambda 2, all we are doing is reproduce the original constraints. So, dl by d lambda 1 is equal to 0 will give me x 1 minus x 2 is equal to 0, and x 1 plus x the dl by d lambda 2 is equal to 0 will give me x 1 plus x 2 plus x 3 minus 1 is equal to 0. These are in fact the original set of constraints. So, you got 5 equations now, and there are 5 unknowns x 1, x 2, x 3 and lambda 1 and lambda 2. There are 5 unknowns. We solve these 5 equations simultaneously and get the values of lambda 1 and lambda 2. So, we reproduce these equations x 1 plus lambda 1 plus lambda 2 is equal to 0. Look at these. So, these equations I am reproducing. So, these are the 5 equations in 5 unknowns. We solve these equations. I leave the solution to you. The solution comes to x 1 is equal to 1 by 3, x 2 is equal to 1 by 3, x 3 is equal to 1 by 3 and lambda 2 is equal to minus 1 by 3 and lambda 1 is equal to 0. So, this is the set of solutions. So, you get x star as 1 by 3, 1 by 3, 1 by 3, this is a vector, and lambda star which is lambda 1 and lambda 2 is 0 and minus 1 by 3. So, this is how you get the stationary points where the necessary conditions are satisfied. Now, we need to examine whether the stationary point that we obtained thus in fact corresponds to a maximum or a minimum value, for which we have to look at the sufficiency condition. So, in the sufficiency condition, we deal with the second order derivatives of the Lagrange function with respect to the variables x 1, x 2, etc., and the first order derivative of the constraint function with respect to each of the variables. So, we formulate the determinant D as L11 minus Z, L12, L13. There are 3 variables 1, 2, x1, x2 and x3. Similarly, we have 3 constraints and 2 variables. We have 3 variables and 2 constraints. So, this is the first constraint, partial derivative of the first constraint with respect to first variable, second constraint with respect to first variable, first constraint with respect to second variable, second constraint with respect to second variable, first constraint with respect to third variable, second constraint with respect to third variable, and then the transpose of this G11, G12, G13, G21, G22 and G23. This is G22 here and G23, and this determinant we equate it to 0 and then solve for it. So, we get the values now. L11 is d square L by dx1 square, dl by dx1 we know x1 plus lambda 1 plus lambda 2. We take the second order derivative with respect to x1. So, you get 1 here. Similarly, d square L by dx1 dx2, that becomes 0. Then d square L by dx1 dx3, that becomes 0. Similarly, d square L by dx2 dx1 is 0, d square L by dx2 square is 1, d square L by dx2 dx3 is 0. Then we go to the third variable, dl by dx3 is x3 plus lambda 2, then d square L by dx3 dx1 is 0, d square L by dx3 x2 is 0, d square L by dx3 square is equal to 1. Similarly, we look at the constraints. G1 of x is x1 minus x2 is equal to 0. So, G11, which is the first constraint with respect to first variable, dg1 by dx1 is equal to 1. First constraint with respect to second variable, dg1 by dx2 is equal to minus 1. First constraint with respect to third variable, dg1 by dx3, which is equal to 0. Then the second constraint is x1 plus x2 plus x3 minus 1 is equal to 0. So, we take the second constraint with respect to first variable, partial derivative of the second constraint with respect to first variable, which is 1, second constraint with respect to second variable, which is 1, second constraint with respect to third variable, which is 1. So, we have obtained the second order derivatives of the Lagrange function and the first order derivative of the constraint functions. So, let us formulate the determinant D. So, determinant D is 1 minus z, we are using these values now, this is 1, 0, 0. So, using these values now, I will put the constraint the determinant as 1 minus z 0, 0, 1, 1, 0, 1 minus z 0, minus 1, 1. I am using these values now, minus 1 is here and 0 is here. So, we formulate the determinant D as written here, equate the determinant to 0. Then you get a polynomial of the order of n minus m. N is the number of variables, in this case it is 3, m is the number of constraints, in this case it is 2. So, we can use any of the classical methods of solving determinant, or we can use the MATLAB directly to solve this for z. So, you get z is equal to 1 in this particular case. So, you have a polynomial of order 1 and therefore, there is only one root possible here, namely z is equal to 1. This is a positive value. So, you have only one root which is positive, and therefore, what should it correspond to? Positive values in sufficiency condition always correspond to a minimum value, and therefore, the point x star lambda star in fact corresponds to a relative minimum. So, as the root is positive, the stationary point which is 1 by 3, 1 by 3, 1 by 3, this is our x star, is a local minimum of f of x. And then we substitute these values in our original function and get the f minimum as 1 by 6. So, this is how we use the method of Lagrange multipliers when we are optimizing a function f of x of n number of variables x 1, x 2, etc., x n subject to equality constraints g j of x is equal to 0, j is equal to 1, 2, etc., m number of equality constraints. Now, in most of the engineering decision making problems, engineering optimization problems, we do not have the luxury of having all equality constraints, and therefore, we may not be able to use the Lagrange multiplier method directly. We will be in general dealing with a general problem statement, general problem of the type maximize or minimize f of x subject to g j of x less than or equal to 0. There are inequality constraints. So, the most general formulation of a optimization problem is maximize or minimize f of x subject to g j of x less than or equal to 0, and in fact, g j of x can be greater than or equal to 0 also, depending on how the problem is formulated. For this general statement of the problem, there is no single algorithm which takes care of various specific cases that arise out of this general statement of the problem. For example, some of the constraints can be equality constraints, some of the constraints can be less than or equal to, some may be greater than or equal to, some of them may be non-linear constraints. The objective function can be non-linear, objective function can be convex, the set of constraints can be convex, can be concave, and so on. So, there are large number of cases that arise, and there is no single algorithm or single method by which this general problem can be solved. However, all optimization problems stated in that general form must satisfy certain necessary conditions for them to have an optimal value at a particular point, at a particular stationary point. Indeed, all optimization problems that are formally stated must satisfy these necessary conditions, and these are called as the Cohen-Tucker conditions, or abbreviated as the KT conditions, and in fact, more generally they are also called as KKT conditions after the mathematicians who have formulated these conditions. Any optimization problem must in fact satisfy these conditions, KKT conditions or KT conditions. We will stick to the notation KT conditions, Cohen-Tucker conditions. So, let us see what are the Cohen-Tucker conditions. Now, the Cohen-Tucker conditions can be stated for a general optimization problem. So, we will state this for the problem minimize f of x subject to g j of x less than or equal to 0. So, this is the condition that this is the optimization problem that we are stating. We are looking at the minimization of the function, and we are stating the conditions in the form g j of x less than or equal to 0 for all j 1, 2, etc., m. For this combination of the objective function and the constraints, the Cohen-Tucker conditions can be stated as follows: df by dxi, which is the first partial derivative of the original objective function with respect to the ith variable, df by dxi plus summation j is equal to 1 to m. You have m number of constraints, lambda j dgj dxi, which means the jth constraint with respect to ith variable. Remember, we are writing this condition for a given I is equal to 1, 2, etc., n. So, for a given I, first partial derivative of the objective function f with respect to ith variable xi plus summation j is equal to 1 to m lambda j dgj, that is the jth constraint differential of the jth constraint with respect to ith variable for which we are writing this constraint equal to 0. So, this is the first set of conditions df by dxi plus j is equal to 1 to m lambda j dgj by dxi is equal to 0, and this condition we write for all I is equal to 1, 2, etc. n. So, you get n number of such conditions. Then the second set of conditions are simply lambda j gj is equal to 0. So, you have the original constraints gj of x less than or equal to 0, multiply with respect to multiply with lambda j, which are in fact the Lagrange multipliers. We will see that in linear programming lambda j is gj is equal to 0, and this we write it for all the condition, all the constraints j is equal to 1, 2, etc. m. So, you get m equations here. So, you get n conditions here and m conditions here. Then we have the original constraints gj of x less than or equal to 0, and for this combination which is minimization of f of x and subject to gj of x less than or equal to 0, your lambda j's must be greater than or equal to 0. So, you have j is equal to 1 to m. So, you get n equations here, you get m equations here, you get m conditions here and m conditions here. So, you have n plus 3m conditions, n plus 3m equations. How many variables you have? You have n plus m variables, namely the first the original n decision variables x1, x2, etc., xn. So, you are writing this for n different variables, one condition associated with each of the variables, and the lambda j's, lambda 1, lambda 2, etc., lambda m. So, you have n plus m variables. So, the way we apply these Cohen-Tucker conditions is, we use the first n plus m equations, these sets of equations, and solve for the n plus m variables, namely x1 plus x2 plus x1, x2, etc., xn, and lambda 1, lambda 2, etc., lambda m. So, you solve for the n plus m equation, n plus m variables using the n plus m equations. Then you use the other conditions, namely gj less than or equal to 0 and lambda j greater than or equal to 0, to verify which among these n plus m, which among these various sets of n plus m values that you would have obtained in fact satisfy these conditions also. So, we solve using the first n plus m conditions, we solve for the n plus m variables and check the other two conditions, check whether these solutions in fact satisfy the other two conditions. So, this is how the Cohen-Tucker conditions are stated and used for optimization problems. Remember again that the lambda j greater than or equal to 0 depends on this particular combination, minimize f of x subject to gj of x. So, when you have these particular combinations, the lambda j will be greater than or equal to 0. Gj less than or equal to 0 just depends on the original conditions, original constraints. If gj of x greater than or equal to 0, here it will be gj of x greater than or equal to 0. The sign of the lambda j, however, will depend on what kind of combinations we have here, minimize subject to less than or equal to, maximize subject to less than or equal to, minimize subject to greater than or equal to, maximize subject to greater than or equal to. So, depending on these, the sign of the lambda j's will change. This condition is simply reproduction of the original constraints, and these will remain the same. These two conditions will always remain the same irrespective of the combinations. Here we are taking the first order derivative with respect to each of the n variables, and this term is simply with respect to of the jth constraint, partial derivative of the jth constraint with respect to ith variable multiplied by the Lagrange multiplier of that particular constraint. Remember, lambda j is associated with the constraint gj. So, this condition remains the same irrespective of the combination here. This condition is simply lambda j into g j equal to 0. This condition remains the same irrespective of the combination here. This condition is simply reproduction of the original set of constraints. Only this condition, which is lambda j, whether it is greater than or equal to 0 or less than or equal to 0, depends on the particular combination. So, I have stated this here for minimize f of x subject to g j of x less than or equal to 0. For that, lambda j's are greater than or equal to 0. I will now state this also for other combinations. Let us say that you have a combination, I will write all the combinations. So, if you have minimize f of x subject to g j of x less than or equal to 0. This is the problem that I just stated. For this problem, you have lambda j greater than or equal to 0. If we change one of them, let us say from minimization I make it maximization, but retain the other condition the same, then lambda j will reverse the sign. If we change both of them, then lambda j's will still be greater than or equal to 0. I repeat, here we are talking about minimize f of x subject to g j of x less than or equal to 0. If I change one of them, from minimize I make it maximization, however, I retain g j of x still less than or equal to 0, then lambda j's become negative. If I change one of them, lambda j's will reverse the sign. If I change both of them, that is I make maximize f of x subject to g j of x greater than or equal to 0, I have changed both of them, then lambda j's will still remain the same. So, we will write them more formally. I will change the first one, that is this is the first form. In the second form, I will write maximize f of x subject to g j of x less than or equal to 0. So, the constraint I have not changed, but the objective function I have changed. From minimize I will write to I have written as maximize. In this case, lambda j will be less than or equal to 0. Now, the third one, I will retain the objective function the same, minimize f of x, but I will change the constraint, that is subject to g j of x. Instead of less than or equal to, I will make it greater than or equal to. Because I changed one of them, your lambda j in this case will be greater than or equal to 0. I am sorry, with respect to this we are talking about now minimize f of x g j of x less than or equal to 0 and lambda j is greater than or equal to 0. If we change either the objective function or the nature of the constraint, then lambda j's will reverse the sign, and therefore, in this case the lambda j will be less than or equal to 0. If we change both of them, namely I will make the minimization function as maximization function, that is objective function as maximize f of x, and I also change the constraints from the original less than or equal to, I make it greater than or equal to. So, g j of x I will make it greater than or equal to. Because I have changed both of them, the original sign of the lambda j's remain, namely lambda j greater than or equal to 0. So, this will indicate the Kern-Tucker conditions for all possible combinations. Objective function minimization, constraints less than or equal to 0, then lambda j's are greater than or equal to 0. Objective function maximization, constraints less than or equal to 0, lambda j's will be negative. Objective function minimization, constraints greater than or equal to 0, then lambda j's must be negative. Objective function maximization, constraints greater than or equal to 0, then lambda j must be greater than or equal to 0. So, just remember one of them, that is this particular form you remember, minimize f of x subject to g j of x less than or equal to 0, then lambda j must be greater than or equal to 0. Remember one of them, and then if you change one of these, that is either the objective function or the nature of the constraint. If you change one of these, the lambda j's will reverse the sign. If you change both of them, lambda j's will not reverse the sign, will be same as greater than or equal to 0. So, this is how the Cohen-Tucker conditions are formulated, and of course, all the remaining conditions remain the same as I just indicated there. The remaining conditions will still remain unaltered. That means, these two conditions will remain the same. These condition is dependent on the type of constraints that you have. For example, the jth constraint can be greater than or equal to 0, then you put the jth constraint as greater than or equal to 0, and the sign of this will depend on the nature of the objective function and the particular type of the constraint, whether it is less than or equal to 0 or greater than or equal to 0. So, this is how we formulate the Cohen-Tucker conditions for any given optimization problem, and any given optimization problem can be expressed as minimize f of x subject to g j of x less than or equal to 0, or variants of that, that is maximize f of x subject to g j of x less than or equal to 0, or maximization f of x subject to g j of x greater than or equal to 0, and so on. So, for any given general optimization problem, it is possible for us to write down the Cohen-Tucker conditions, and the Cohen-Tucker conditions are the necessary conditions for the function f of x to have a minimum value subject to these conditions, g j of these constraints, g j of x less than or equal to 0. There are certain important aspects that you must remember for the Cohen-Tucker conditions. One is that any optimization problem must satisfy the Cohen-Tucker conditions. The second important thing is Cohen-Tucker conditions are necessary conditions, they are not sufficient conditions. That is, the conditions that we just had a look at, we just stated, are necessary conditions for a local optimum. They are not sufficient conditions in general. For any general problem, they are not sufficient conditions. However, there are certain types of problems called as convex programming problems, where these conditions can also be sufficiency conditions. So, KT conditions are necessary conditions. And any optimization problem must satisfy the necessary conditions. They are also sufficient conditions for what are called as convex programming problems. That is, you are looking for a minimization of the function, that is f of x is a convex function, your objective function is a convex function, and all your constraint functions g j of x, they are all convex functions, and you are looking for a minimization of the function. Such problems are called as convex programming problems. So, these are this is a specific case of the general optimization problem that we dealt with. So, if you have f of x as convex and g j of x also as convex, all constraints are also convex functions, then the Cohen-Tucker conditions that we just stated are both necessary as well as sufficient conditions. So, this is what you must remember. So, Cohen-Tucker conditions are both necessary as well as sufficient if you are dealing with convex programming problems. And how do we use this? We state the Cohen-Tucker conditions depending on the nature of the objective function, whether it is minimization or maximization, and the nature of the constraints g j of x less than or equal to 0 or greater than or equal to 0. We use the first n plus m conditions to solve for the n plus m variables, and then check the other two conditions, namely g j of x less than or equal to 0 and lambda j g j equal to 0, to verify whether I am sorry, Gj of x less than or equal to 0 and lambda j greater than or equal to 0 to verify whether the n plus m variables that you obtained in fact satisfy the other two sets of conditions. So, we use this to solve for the n plus m variables and then verify whether the solutions that you obtain in fact satisfy these conditions. You may in general have multiple number of solutions, and some of the solutions may satisfy all the conditions and some of the solutions may not satisfy some conditions. And therefore, you choose only those solutions among a number of solutions that you obtained. Only those solutions which satisfy all the conditions are in fact chosen, they in fact satisfy these necessary conditions, and they lead to local minimum or local maximum. Again, these are necessary conditions and not the sufficiency conditions. So, we will examine through an example how these Cohen-Tucker conditions are applied. We will do that in the next lecture. So, essentially in today's lecture, we started off with equality constraints, that is optimization of a function subject to equality constraints. And in the previous lecture, we had dealt with the method of direct solution. In today's lecture, we introduced the Lagrange multiplier method, where associated with each constraint, we introduce a variable called as a Lagrange multiplier. So, you have m number of constraints, therefore, you will have m number of Lagrange multipliers. We then formulate a Lagrange function and formulate the necessary conditions of the Lagrange function. The basic premise and the principle here is that the Lagrange function is so formulated that if you optimize the Lagrange function, the original function itself is optimized. So, associated with each of the arguments of the Lagrange function, the necessary condition is obtained by differentiating the Lagrange function with respect to each of the arguments, that is x 1, x 2, etcetera, x n and lambda 1, lambda 2, etcetera, lambda m. Then we formulated the sufficiency condition. We wrote down the sufficiency condition, we did not formulate, we have just used the sufficiency condition through the determinant d, and I have just explained how to formulate the determinant d based on the second order derivatives of the Lagrange function with respect to each of the original variables x 1, x 2, etcetera, x n, and the first order derivative of each of the constraints d g j by d x I. So, the jth constraint derivative with respect to the ith variable, and then using these we formulate the determinant d, equate it to 0. It gives a polynomial of order n minus m in the variable z. If all the variables, if all the roots of this polynomial are positive, then the stationary point corresponds to a minimum. If all of them are negative, it corresponds to a maximum. Then we went on to formulate the state, the Cohen-Tucker conditions for any given general optimization problem. The Cohen-Tucker conditions are necessary conditions and not sufficient conditions. Any optimization problem must satisfy the Cohen-Tucker conditions. In cases where the objective function f of x is convex as well as the constraints are all convex functions, then the Cohen-Tucker conditions also are sufficient conditions. So, we will continue this discussion in the next class by starting off with a example problem. Thank you for your attention.